Welcome, y'all. Remember, like I said yesterday, we're going to spend a couple days talking about this Tomas Pueyo article, Coronavirus Why You Must Act Now. And remember, the basic conclusion here is that we need to be socially distancing as much as possible. Where by social distancing, we mean deliberately increasing the physical space between ourselves and others to limit the spread of COVID-19. So basically, if you can, stay home. If you can't, then try always to remain at least 6 feet from others. And if you can't do that, please be doing what you need to do to clean, disinfect, sanitize your area to protect yourself and others. Because if we don't do this social distancing, then there's this issue that we will run into these sad and horrible consequences I talked about yesterday. So let's get into it.
As straightforward as this argument from Pueyo might sound, there's a lot of complex work from lots and lots of different researchers from lots and lots of different disciplines that go into this argument. So, like I said, for the next couple days, I'm going to be breaking this down discipline by discipline, and today we're going to focus on some of the mathematics behind Pueyo's arguments in Coronavirus Why You Must Act Now. So I've been told to expect that anything longer than 10 minutes, nobody's really going to pay attention to. So I'm going to try to just focus on what I think are the most essential mathematical concepts from Pueyo's article that are relevant to things that people are really talking about with respect to the coronavirus right now. And the first is going to be something from arithmetic, from the theory of numbers, where we'll make a distinction between linear and exponential growth in a series of numbers. And this is really relevant to the fact that people have been talking about the fact that the number of COVID-19 cases is growing exponentially rather than linearly. The second we'll talk about will move us more directly into geometry, where we study things like shapes, slopes, and curves. And this is particularly relevant for the fact that folks have been saying over and over and over again what we need to do, why we need to socially distance is to flatten the curve. So we'll talk about what that means there. And these are the only two things we'll focus on here, but it's important that even just developing the conversation from these two things could lead us into lots and lots and lots of different parts of mathematics, could lead us into analysis, into topology, regression analysis, statistical modeling, and logic more generally. And these are all things that I actually know something about. Some of the things we'll talk about over the next couple days I don't know so much about, but this is one where if you do happen to want to talk about some of these things more, please let me know. As far as exponential growth in Pueyo's article is concerned, chart 2 here shows what people are talking about most clearly. So chart 2 is a graph that shows us the total number of cases of COVID-19 infections outside of China between late January and early March. Now, notice from January 22nd to late February and early March, the number of cases grows very gradually, and then all of a sudden takes a really, really sharp turn upward, such that if you look at the total number of new cases between March 2nd and March 10th, you see that's about 30,000 new cases, right? At March 10th, there's roughly 40,000 cases, and at March 2nd, there's roughly 10,000. So that means there were 3 times as many new cases in the week plus between March 2nd and March 10th as there was between the 6 weeks between January 22nd and March 2nd. And this is what we need to understand here when people are talking about exponential growth. When this coronavirus gets to a new area, it will grow gradually at first, and then it will suddenly take a sharp, sharp turn toward there being more and more cases piling up. And this is the growth we need to be taking measures to avoid. Now, if you really want to understand the significance of saying that the number of COVID-19 cases is growing exponentially, I think we need to give a context here. Context helps us understand better and gives us significance. So, if we want to put exponential growth in context, we need to look at growth generally, and we need to be able to contrast exponential growth with other types of growth. which we'll really see is just about understanding the difference between multiplication and exponentiation as two different operations on numbers. So, taking a look at growth generally, first we need to think about the fact that growth is generally a type of change. When my hair grows, it changes from being one length to being a different length. And change, speaking as a philosopher here, is a surprisingly sophisticated concept because change involves sameness through difference. And sameness and difference are really sort of the fundamental concepts we use. So when something changes, when I change from having no hair to having the really long hair I have now, we say I have stayed the same through that process, even though some property of mine is different than it used to be. Now, growth is a particular type of change, though, where growth requires a measure of that change and values that we think of in terms of positive and negative. Because growth requires a change in value in some positive direction. So once we start adding measures and numbers to changes, then we're talking about growth. Hence, we realize here that growth is something that ultimately belongs to arithmetic, where arithmetic is the study of numbers, relationships between numbers, operations on numbers, and functions between different numbers. When we're looking at sequences of numbers, these can have all different kinds of properties. They can be random sequences of numbers like this one here. They can be constant sequences of numbers where one number is the same as the next is the same as the next. Now, getting closer to exponential growth, which as I said earlier is often contrasted with linear growth, a sequence of numbers can linearly decrease. For example, take a look at this sequence of numbers here. 27, 24, 21, 18, 15, 12. Those are decreasing numbers. Each one is smaller than the last, but they're also decreasing in a particular way. Namely, each one is exactly 3 less than the one prior to it. That constant rate of change makes it linear change. The fact that the rate is negative means it's decreasing linearly. So linear growth, then, is change just like this, but in a positive direction. For instance, take this sequence of non-negative even numbers. Each one is larger than the previous one. Each one is exactly 2 larger than the previous one. That constant rate of change of increase means we have a case of linear growth. Previewing what we're going to say about exponential growth, notice that we can come up with this sequence of numbers by letting each entry, a sub n in the sequence, be equal to 2 times n for all n greater than or equal to 0. So 2 times 0 is 0, 2 times 1 is 2, 2 times 2 is 4, 2 times 3 is 6, and so on. Exponential growth, on the other hand, is represented by this last sequence of numbers. 1, 2, 4, 8, 16, 32, 64, and so on. Here, the change is similar to the previous one in that it is constantly growing, but it grows in a very different way. The rate of change itself changes. It starts off gradually, with the third entry in both sequences being 4, but then suddenly takes a great leap, with the 7th entry in the exponentially growing sequence being 64, and only 12 in the linearly growing sequence. This can be represented by the fact that each entry in this last sequence, a sub n, is 2 times the previous entry. Or another way we can represent this is by saying that each entry, a sub n, is 2 raised to the exponent n for all n greater than or equal to 0. So, 2 to the 0 power is 1, 2 to the first power is 2, 2 to the second power is 4, 2 to the third power is 8, 2 to the fourth power is 16, and so on, and that's exponential growth. Next, as I said, we're going to be talking about mathematics in relation to flattening the curve. And here's a really good example that explains really clearly in a short amount of time the way in which people are using this phrase, flatten the curve, in relation to COVID-19.
Governments across the globe are scrambling to contain the spread of COVID-19. Now, you may have heard experts talking about efforts to flatten the curve. But what does that actually mean? Well, the curve that experts refer to is a graph like this one, which adds up the number of COVID-19 cases over time. Now, without preventive measures, there could be a spike in cases. Now, that's the red curve that you see over here, and that would overwhelm national healthcare systems with patients, and that's basically what we're seeing in places like Italy right now. But if we can delay the spread of this virus over the course of weeks or perhaps months, we would be able to flatten that curve. Now, that's the blue line that you're seeing on the screen. The slope a lot more gentle in that instance. Now, the healthcare systems should then be able to manage and treat all patients as quickly as possible. This would also give healthcare professionals the time that they need to develop treatments and eventually, we hope, find a vaccine. Now, that's why governments have encouraged social distancing, as an example, imposed those city lockdowns, school closures, as well as restrictions on international travel. Research shows that the faster authorities respond, well, the more lives are going to be saved. Singapore and Hong Kong are examples of places that quickly implemented those strict quarantine rules, and that's probably why the increase in infections in these cities has been slower. Whereas the rapidly rising case numbers in South Korea, the United States, Italy, as well as Iran, could point to a delayed response to the outbreak.
To really understand the flattening of curves, we need to understand some context for curves generally. And when we're looking at curves with respect to mathematics, we're talking about geometry. Because geometry generally studies shapes and the spaces we find them in. That said, when people study geometry today, they're really doing it in a complex way that involves what we call analytic geometry, where there's a coordinate system of places in space being marked by numbers. That is, each point in space is associated with x and y coordinates. And this is really fun to bring up analytic geometry because you just can't tell the history of analytic geometry without talking about Muhammad ibn Musa al-Khwarizmi and Omar Khayyam, who were two phenomenal scholars of the Islamic Golden Age, one of my very, very favorite topics in relation to intellectual and cultural history. So I'll have to at some point turn one of these videos into something on the Islamic Golden Age. But anyway, the key to connecting flattening curves and rates of change of curves involves looking at the slope of certain lines. Now, for those of you who don't remember, the slope of a line is what you get when you take 2 points on the line, subtract those two associated y coordinates from the points on that line, and divide it by the change in the two x coordinates from those points. And we can think of this as representing how fast the particular graph is changing. So looking back to the bottom left part of this slide, here we have one line and a second line where the first has a greater slope than the second. That is, the first line is increasing at a greater rate than the bottom one is. Now, what do we do when we've got a curve like this red one, which represents exponential growth? Because there, we'll get very different slopes of lines depending on which 2 points we pick. So what we do here to talk about the instantaneous rate of change at a particular point on the curve is look at the slopes of lines tangent to the curve. So remember, tangent lines are those lines which are just close enough to the curve to touch it at just 1 point. So here are 2 lines tangent to this curve at different points. Now notice though, this curve is not flattened. And we can see this by the fact that the first tangent line has a lesser slope than the second one. So, what we mean by flattening the curve is having tangent lines which decrease in slope from one to the next. For COVID-19, that would mean having fewer and fewer new cases from day to day. We want that. We want to flatten the curve, and we do so by social distancing. So that's all the mathematics I'm going to talk to you about for today. But I really want to encourage you to learn more mathematics. As far as I'm concerned, the very best motivation for learning more mathematics possible is Mos Def's song Mathematics. If you do not know this, please listen to it. It's absolutely fucking amazing. Now, my wonderful friend and brilliant colleague, Dr. Claudia Ford, suggested to me that sincerity, being real, is what's going to make these videos work. So, on that front, I thought I'd give you a little treat here. Now, I am absolutely obsessed with music generally, but rap in particular. I absolutely love to rap. So, here you go. Check it, 1 for Charlie Hustle, 2 for Steady Rock, 3 for the forthcoming live future shock. It's 5 dimensions, 6 senses, 7 firmaments of heaven and hell, 8 million stories to tell, 9 planets faithfully keep an orbit with the probable temp. The universe expands length. The body of my text possess extra strength. Powerlifting powerless up out of this towering inferno. My ink so hot it burned through the journal. I'm blacker than midnight on Broadway and Myrtle. Hip-hop past all your tall social hurdles like the nationwide projects, prison industry complex. Working class poor, but it keep you alarm set. Streets too loud to ever hear freedom ring. Say evacuate your sleep. It's dangerous to dream, but your chain cats get they chapow. Who dead now? Killing fields need blood to graze the cash cow. It's a numbers game, but shit don't add up somehow. Like I got 16 to 32 bars to rock it, but only 15% of profits ever seen my pockets. Like 69 billion in the last 20 years spent on national defense, but folks still live in fear. Like nearly half of America's largest cities is 1/4 black. That's why they get Ricky Ross on the crack. 16 ounces to a pound, 20 more to a key. A 5-minute sentence here and then you're no longer free. 40% of Americans own a cell phone so they can hear everything that you say when you ain't home. I guess Michael Jackson was right. You were not alone. Rock your hard half black cause you in the terror dome.